All right, people. So welcome back. Let's talk about compound interest. This is a great practical application of an exponential function. Uh, so we've got here this little formula. This looks like a lot of alphabet soup, does it not? So it says A equals to P times the quantity 1 plus R over N, all raised to the power of N times T. So what does all this stand for? Well, the letter P stands for what they call the principal, which is the amount that you might invest, say, in a bank. Okay. The letter R stands for the interest rate. And typically it will be stated to you as a decimal, like, 1.5% or something. Or sorry, it'll be stated to you as a percent, like 1.5%. But you'll write it in a decimal, like 0.015 in that case. Okay, N is the number of times that interest is compounded per year. And T is the number of years that you let your money sit there. And A gives you the new amount that you have after this amount of time T has passed. So what's going on here? The idea is you go to a bank and you put your money in the bank, your principal, and then they let that money collect interest at a sort of rate. So every compounding period, they apply this interest rate to whatever you have. So they say, okay, well, let's take that much of what you have now in the bank and add that to your account. And if you let that continue over some number of years, you can have more and more money in there, which is then gives you an exponential function of time, right? Okay, and so what are some of the common compounding periods? There's annually, which means that n equals 1, they compound once a year. Semi-annually, which means they compound twice a year, so n is 2. Quarterly is 4 times a year. Monthly is 12 times a year. And daily, I guess we'll say, is 365 days a year. Although, yeah, we're going to ignore leap years, and I don't really know what businesses actually do if they count work days or weekend days. I don't know. We'll just pretend like this is what's going on for this. I think most commonly are probably quarterly or monthly, so that's fine. So this example asks us to find the amount in a savings account after $2,000 is invested at 5% interest compounded monthly for 3 years. So P is 2,000. That's the amount that was invested initially. 0.05 is the interest rate. The compounding periods are 12. It's compounded monthly. And the time, T, is 3 years. So T is 3. So the new amount that we have, we can take to the Texas Instrument probably and find out. We'll have 2,000 times the quantity 1 plus 0.05 divided by 12, all raised to the 12 times 3. So the only change I made from this first step to the next one was that I made 12 times 3 is 36. And now you'll want to take to your Texas Instrument probably to compute this value. And I got roughly $2,322.94. And so that's more money than you had initially invested, right? And so the total interest that you earned over that course of that 3 years is the difference. So the difference here is $322.94. That's money that you made by just having your money in there to begin with. Okay, the next example asks us, how much should be invested in an account that earns 2.5% compounded semi-annually so that it has 3,000 after 4 years? So now they're asking us, how much principal should we start with to get $3,000 as our new amount after 4 years, where the interest rate is now 0.025 and the compounding periods, the number of them, n, equals to 2. So we'll set up this equation that we would like to have $3,000 at the end. We don't know what this principal is, so we'll put that there. I made a little bit of a pen mistake there. Ooh, a penno. Oops. Anyway, so just ignore that. And then we have 1 plus 0.025 divided by 2, all raised to the product 2 times 4, which is 8. Okay. And so what I did here was just take this ugly number, whatever it is, get it in your Texas Instrument, and then divide 3,000 by that ugly number. And what you get then is that P equals to roughly $2,716.20. So if you invested just this much, then in 4 years at this rate and this number of periods, you would have $3,000. Okay. The next topic is about continuously compounded interest. This is like having interest just compounded all the time. Okay, well, this is a little crazy, but we'll just take it. The formula for this is the new amount equals P times E to the RT, where E is that famous number I mentioned at the end of the last video. So this example here asks us how much is in an account that earns 9% compounded continuously for 5 years when $700 is the initial amount invested. So we'll just go ahead and plug away here. So 700 times E to the interest rate is 0.09. And now there is no number of compounding periods. That's like assumed to be almost like infinite of sorts. So we'll just have 0.09 times 5, which is 0.045. And if you plug this guy into your Texas Instrument, you'll see that you have something like $1,000, $1,097.82. All right, so that was good. The next application of exponential functions is a classic one. It's about Halflife. This is about exponential decay. This last example about money, we would hope would be exponential growth, right? Exponential decay is typically these things are brought to us from the land of like chemistry or something like that. So we have some kind of substance and it's being exposed to the elements and it's decaying, and the half-life of a substance is something that is the amount of time that it takes for there to be only half of what was originally there left. So if you start with some initial amount, what they call A0, then you want to know what is the half-life, what is the time it takes to have half of that A0 left over. That's what they call the half-life. And so here we have this expression for exponential decay of a substance like this. What we'll write is that the new amount that's left over at any time t in between there is the initial amount times 1/2 to t divided by the half-life. Okay? So let's see what's going on. So they say in this example, the half-life of strontium-90 is 29 years. And some scientist has 40 milligrams of that stuff. And you want you to know what is a model, an exponential model that gives the amount of strontium-90 that scientist has after t years. This is assuming they're just letting it sit there and be exposed to the elements and decay. So we'll take our cue from what's above. They say that the half-life is 29 years. We'll keep everything in years here. And we'll write that our new amount, A of t, equals to 40 times the quantity 1/2 raised to the power of t divided by 29. Okay? So that when we've gone for 29 years, we've gone what they call 1/2 life. So we would hope that we would have at that point then 20 milligrams left. Let's make sure that the formula makes it work that way. So that A of 29 is 40 times 1/2 to the power of 29 over 29. Well, 29 over 29 is 1, and 1/2 to the 1 is 1/2. So 40 times 1/2 is, in fact, 20. So we'll have 20 milligrams there. Okay, how about 58 years? Well, and you might know that 58 is 2 times 29. So now that's talking about going 2 half-lives. That is to say that after 1 half-life, we only have 20 milligrams. Now after another one, we'll only have half of what that 20 was. So we should anticipate the answer will be 10. But let's make sure that the formula makes it work out. So we have 40 times the quantity 1/2 to the 58 over 29. That is to say 40 times 1/2 squared. But 1/2 squared is 1/4. And 40 times 1/4 is 10. Very nice. Okay, and then this last one is a little bit different. They don't give us a number that is a multiple of 29. That's fine. We'll just have to take to our Texas Instrument for this guy. So they ask us how much strontium-90 is left after 200 years. And that is the new amount after 200 years is 40 times 1/2 to the 200 over 29, which my Texas Instrument told me was roughly 0.336 milligrams. Okay. And sort of similar, brought to us from the sort of land of biology, is this exponential growth population, or sorry, this exponential function application known as population growth. So here we have some initial population of, say, people or animals or bacteria, I don't know what, and we want to model its growth over some period of time. And so they typically will give to us some number R in a percentage, which is a growth rate. That is a growth rate, I guess, per unit of time. So if we take T in years, this growth rate is a percentage per year that the population is increasing. And then the formula for our new population at any given time T then is our initial population, they call P0, times the quantity 1 plus R to the T. So they tell us here in example 11 that the population of a city in 2010 was 5,600, and it is growing at a rate of 2.1% per year. So we'll take T equals 0 to correspond to the year 2010. Because we don't know anything, they don't tell us anything about what was happening before then. So we'll just pretend like that was the sort of start of time for this scenario. Okay, and so the initial population is 5,600, and then that growth rate is 0.021 because it's 2.1%. So then we'll plug this into this guy and we get 5,600 times 1 plus 0.021 all raised to the T. But you can simplify 1 plus 0.021. That is just 1.021. So we get 5,600 times 1.021 to the T. And now they ask us how many people will be in the city in 2016. Well, 2016 is 6 years after the initial time, so that will correspond to the time T equals to 6. And so we can plug away in our Texas Instrument that P of 6 is 5,600 times the quantity 1.021 to the 6th. And if my Texas Instrument told me right, this one is around 6,344 people. Okay, and that will do it for this talk. Come back and we will meet the inverse of exponential functions. They are called logarithmic functions. As you notice, the exponential functions we met today were all 1-to-1, so they should have an inverse. So we'll hear more about that next time.